So, hello everybody. I welcome you to our webinar, today's webinar, Statistics and Measurement Uncertainty in XRF. My name is Rainer Schramm, and I would like to guide you today to quality control in XRF to show you a little bit how we are getting our XRF method under control. Like always in our webinars, you have the possibility to put your questions into the chat, and I will try to answer them either during the webinar or at the end. Then let's start. Like always, when we talk about statistics, we have to clarify some terms. And the ones I want to discuss today is the measurement error in XRF, the repeatability, reproducibility, trueness, or other word bias, accuracy in comparison to trueness, limit of detection, limit of quantification, and measurement uncertainty. Yeah, so these are all the terms we have to clarify because they will be involved in this kind of control. There's a question if you can have this presentation. Yes, it will be recorded as video, and you will get the link after we have recorded it. So I would recommend that for further literature, that you have a look into the Nortis reports 569, which is describing very well the internal quality control, and the 537 is describing measurement uncertainty. Both give you very good indication how to do these calculations, and there are free downloads available. So this is the base of our work and where I got a lot of information from. So let's start with our measurement error in XRF. Here you see a peak, a classical peak, in this case from kappa k alpha. And the measurement principle in XRF is counting pulses. And this means that the X-ray can be seen as particles covered by an energy. And these quants, which they are called, they are just counted. So that in the end you have a total number of counts n, and the error of this counting process is the square root. That means when you count during a certain measurement time and the count is increasing, of course also your error is increasing, but not with the same proportion. That means relatively the error is getting smaller with more counts. And this you can see here that, for example, if you have 1 million counts, you have a relative error of 0.1%, because you take the square root and then you put it into relation to 1 million. And if you have only 1,000, you have 3% relative error. Yeah, so as longer you measure, as smaller is your error. And this is an information you can get normally from every X-ray software. That means that you find out what is the intensity of your signal, and intensity in X-ray means the total number of counts. So then you can calculate yourself your measurement error, and you know immediately if this will be in agreement with the specifications or the analytical need you have for your application. The second thing we have to look into is the repeatability. And normally a repeatability is determined by just measuring one sample and several times. And then you get here like this kind of distribution. And either you have a high precision, then the points are very close to the mean value, or you have a low precision, and then of course you have a very high distribution. And this we call random error. And the random error, or this determination of the repeatability, is linked to that you measure in a short period of time, in one laboratory, with one user, and at one XRF instrument. And that will give you just the error in a very short time period. While when we look into the reproducibility, we still have a random error, but there we look on a longer time with different XRF instruments, with different persons and different laboratories. So like, for example, a proficiency test or a round-robin study, yeah, where you have all these points involved. There's a special case, and this is important for our quality control. That means if you keep the first 3 points, but you measure them in your laboratory, then it is the in-laboratory reproducibility. And this is a very important determination of the random error of your lab for an element, for an application. And this we need to find out if a method is under control or not. While systematic errors or bias, this is related to the trueness. That means you measure a certified reference material, which comes from third party, or a proficiency test sample comes from third party. Then you have your individual measurements, which result in a mean value, and then the difference is called trueness or bias. And such a systematic error could be based on that you measure a different matrix in comparison to your calibration, or you have different sample preparation, different particle sizes compared with the calibration, or you have different calibration ranges, or you just see an aging effect, either of the instrument or of your samples you're measuring. All these could lead to a systematic error, a bias, and then be represented like this. In comparison, the accuracy, which is also a term which is used very often, or even misused very often, means that just a single measurement is compared to the reference value. Trueness is the mean value compared with the reference value, and accuracy is a single measurement and then the difference to the reference value. When we talk about random errors, we always think that they are normal distributed, so that the normal distribution is covering or describing this random error the best. And so we can use then this mathematical base to calculate the mean value with such a formula, and of course the standard deviation of the distribution. However, you have to be careful that you use the estimation of the standard deviation so that you have the n-1 here in the formula. I also put you the Excel functions. So mean value is clear, but here on the standard deviation, you have to be careful that you really use the right function. It's either in the old versions, the stub W, or in the newer versions, the stub W point S. Don't use the n, and because this would be just make the division by n only, and in the laboratory we only have a limited number of values, so this would be never valid. So now let's go into the laboratory, and I give you here a practical example. We measured the cement control sample, which is measured by our raw material program. And in this sample, we measured silicon oxide. And we measured it from February 2018 until February 2019. This was measured several times. And then we calculate the mean value, which is represented by the black line, and we calculate the standard deviation. And by taking the standard deviation, we multiply 2 times, and this represents then a warning limit. And if we multiply by 3, then we have a control limit. So this is now our construction to control our laboratory in the future then. So after February 2019, and this we see in the next picture, we have now used these limits together with the mean value, and now we measured again our control sample. You see from July 19 and then continuously, in principle until today. And we use these limits to check if our method is under control or not. So let's see, for example, here, this point is outside the control limit. So this means our method is out of control and there is some action needed. Yeah? The same here with these 2 points, which are still in between the warning and the control limit, but because it's 2 values after each other, we say this is reason enough to take the method out of control, and we have to check what is wrong. While single measurements, which are just in between the 2 limits, we still consider as an outlier, but our method is still under control. And when the next value is then inside, we just ignore it. We just say this was just an outlier statistically, and we can continue. Another example I wanted to present you is that here we have measured phosphorus again in a cement controlled sample, but now in a cement program. And for cement, we use everything based on the ISO cement method. And the ISO cement method gives us control limits. And so here we don't use the statistically values, so we don't calculate a standard deviation from our measured values. We just have our mean value, and then we use the control limits out of the standard method. And this has the advantage that you see our XRF is much better than the control limits we need, and so we can just let it run. While when we would use here the standard deviation from these values, our control limits would be much closer to the value, and more often than we would have a situation method out of control. And you see now these 2 examples, this one where we use specifications from outside, and this one where we use our own statistical values to determine our limits. These are the 2 extreme situations you have to take into consideration when you build up your quality control system in your laboratory. Yeah? And the problem will be if these limits are too small, you will have very often the situation method is out of control. If they are too far away, like here, you will not see really a trend, and you will have here even outliers, but they are still inside the limit. So your method is always under control. So it is really a question of what is practical in the real world, in your daily work, to have still everything under control, but not too much out of control. So this is just, I wanted to give you these 2 examples that you have an understanding to develop your own method for your laboratory. So here a summary of this method under control issue. Let us think our method is out of control. So the first thing we will do is we will just repeat to measure our check sample. If this is then under control, we know everything is fine. If not, the next thing we could do is that we make a drift correction of our method on the XRF instrument. If then it's good, it's under control. If not, we should repeat our sample preparation. Yeah? So we prepare our control sample completely new, and then we check again if it's under control or not. If not, then this would mean we have a problem with the sample preparation, and we have to go there in all details, yeah, checking all the sample prep machine, and also to check the chemicals we are using. Is there some mismatch, or what is the problem that our sample preparation is not working anymore? When you found it and everything is good, you have it again under control. If not, and you find that now you have a bias, that every preparation gives you a bias to your reference values, then this means probably you have to recalibrate the whole system, yeah, to do a new calibration. Or the other thing is you have completely to redevelop your method because there is a reason you have to find a reason why now your method is not working anymore. Yeah. So if you follow this path, you will have a kind of a guideline to see what you can do to get your method under control. This morning we had the same presentation in German, and there one participant mentioned that he had a situation that there was used a wrong film in the sample preparation, and so he just exchanged it, and then he had it under control. Yeah, so this would have been then here in this part an example. Okay, now let's have a look into limit of detection. How can we calculate this? And the best thing what you can do is that you measure a blank. But what means a blank? I give you an example. You have sand, which is mainly based on silicon oxide. And in this sand, you want to get the detection limit of iron. Yeah, so the best would be you find a pure quartz sand, which has no iron. So let us assume there is 0 ppm iron in that quartz. And now you measure this sample 10 times, and you will get this kind of distribution. That means you calculate from this standard deviation, for example, from 2 ppm. What does this mean? This means that all the values you have found are between -6 and +6 ppm. Yeah, this is your distribution here around your blank value. Now the detection limit is defined that you can distinguish 50% of your determined concentration from the noise, from the distribution around the blank. And this would mean that half of these values you can see, the other half is like noise. And so this would be then be the case when you are 3 times the standard deviation higher. So at 6 ppm, you will have the case, and this would be then our detection limit for this kind of example. When you want to talk about the limit of detection, this is then where your method starts to work. Then you have to go another 3s higher. So then we are around 12 ppm. So that means that now all values are really distinguishing by the noise from the blank value. And if you go to the limit of quantification, then normally what the laboratories are using is 3 times the detection limits, or in this case, it's a 9s until here. So in this way, then you have the full possibility of calculating your lower limit of detection, your limit of detection, and the limit of quantification. So in this way, it's easy to do. What is important in XRF is that you always use a sample where the matrix is correct. So you can't use, for example, an empty sample cup or just a blank glass bead to do that, because then the matrix of your sample is missing, and the matrix is also determining the sensitivity, and that's why it is so important that you use the matrix but without the element. Okay, so then last but not least, we have to talk about measurement uncertainty. What does this mean? Measurement uncertainty is an estimation for the future. That means if you do a measurement tomorrow and you want to tell your customers what is the measurement uncertainty for that value, that means you will determine a result X, and this has an expanded uncertainty of U. But then you have also to specify your confidence interval. Yeah, so what is the probability for this expanded uncertainty? Example, you measure 25.9 with an uncertainty of 0.1 with that confidence interval. What does this mean? This means that in 5% of the cases, your measured value will be outside that limit, or in 19 cases, inside. So this is the estimation you give or you do for your future analysis. And so everybody outside your laboratory has now an indication how good you are able to determine this value. The big question normally is, how can I calculate this value for my daily lab work? And for this, I have made some calculations for you, and now it's going a bit more into mathematics, but I think I will try to explain this as easy as possible. Yeah. So our measurement uncertainty will be based on random errors and systematic errors. So random errors I have described already with our laboratory reproducibility. You remember about 1 year we have measured a control sample, and the standard deviation out of this is our laboratory reproducibility. And this includes, of course, our measurement error of the XRF and the preparation error. And of course, the lab errors like the user and perhaps different XRF instruments. The systematic error is based on the bias we get when we measure a reference material or we contribute in a proficiency test. Here, when we then calculate our laboratory reproducibility, then we take the standard deviation and we calculate it relatively to our mean value. And this is then our relative uncertainty for the reproducibility. For the systematic error, I give you an example for a theorem. There are different parts of contribution for our uncertainty. And the first thing we have to see is that the measurement here has, of course, a distribution. And this distribution has an error, which is here the standard deviation of these values. This standard deviation is divided by the square root of the number of measurements, and this gives you the uncertainty of this measurement error. Then you have the uncertainty of the bias. That means the mean value to the certified value has also an uncertainty. So you take the difference in relation to the reference value. And this gives you then the bias. The third part is the uncertainty you will find in the certificate of the certified reference material. Yeah, and so in this way, you have then three different contributions to your uncertainty of the bias. And this is then by an error addition combined together to the uncertainty of the bias of this theorem. Of course, what you have to consider is that this is only valid for this special concentration, which was measured here, and for this theorem. So that means if you have more than one theorem, you have to do this for every theorem. And if you contribute in a proficiency test, you have to do this also for the proficiency test, and then combine all these bias uncertainties together to the total bias uncertainty. And when you have done this, you will combine this together with your uncertainty of the reproducibility to the total uncertainty. But this, of course, is not the end. We now have to define also the probability of the confidence interval and to say that this is valid in 95% of the cases. So in this case, then we have to multiply it by 2. And then you have your total uncertainty. So this means in the end, you have all these values to calculate your uncertainty for your laboratory, but you have to collect them. Yeah, you have the control chart to collect the uncertainty from the reproducibility, and you have theorems, perhaps you measure on a regular base, and from there, these measurements with the contribution, with the distribution and the difference and the certified values, together you can calculate your bias, and in this way estimate the U. Of course, the calculation for several theorems is not so easy, and therefore I would recommend you that you have a look into this NOR-test report, because there you will find many examples for all these cases I mentioned. And also there's another difficulty, that when in your method there is a concentration range, you have of course to consider more than one concentration, because the uncertainty will change with the concentration. And this you can also see very well in some examples in this NOR-test report. Okay, this was a very quick rush through the statistics for XRF, and now I'm happy to answer your questions. And there is a question here: how do we calculate the LRD and the LRQ and the uncertainty from the information obtained from the calibration curve? In the calibration curve is of course the same information than I have shown you when you measure a blank value. Yeah, because that means calibration samples which are very close to the limit of detection have, of course, the same distribution than a blank value. So if you take the calibration at the very low end, you will find there in the standard deviation the same distribution than in the standard deviation of your blank value. And in this way, then you can easily also calculate from the calibration curve this value. Another question for measurement uncertainty: what about the uncertainty coming from the calibration line? Yeah, this is a good question. When you do it in that way, like I described, then of course the calibration is included for that concentration we consider here. And in the moment you take several theorems which are measured at different concentration, automatically the uncertainty from the calibration is included. If you go the other way around, that for example, you base your uncertainty calculation only on the RMS or SEE of your calibration, then there is a risk that you are too good, yeah, that you haven't included all the error which is only shown in the calibration and not in the laboratory. What parameters should one look at when validating a calibration curve? So the validation of a calibration, I would say that you have to cover the concentration range of a calibration. And if your samples cover different matrices, you also should select different check samples with different matrices. And of course, all these samples should not be part of the calibration. Yeah, they should be really independent. When setting up a new instrument, how do you suggest we set the control limits when there isn't enough data available to set them? This is a very good question, because this is all our problem when we start from scratch. We have no data. Yeah. So then I would recommend that you take a control sample, and for example, on 5 days a week, every day you measure it several times. And then after that week, you already have a small selection of statistics, and then you start to calculate your limits. And then you observe this over the while, and step by step you readjust this, and in this way you get also good experience of your data, and then of course you need the time to set up then the real data. And you will see, as longer you measure, as better is then your data, and as better your control limits will fit to the real laboratory situation. So then there is another question. Our XRF instrument does not report negative values. Should we then, instead of a blank sample, use a low concentration sample for determining the LOD? Perfect question, and you're right, I would do it. Because when you can't see the negative part, it is useless. Yeah, you can't really use it. Yeah, good question. So then we have here another question. We have a calibration covering several matrices. How to select a blank sample for determining the LOD in this case? Okay, normally when you have different matrices, you will have also different elements you are looking at. So you are absolutely right. You have then to determine in each matrix the LOD. And what we do then is that we take the worst one, so the highest LOD, to be safe, that for all different sample, we are on the safe side. Yeah. There's another question. Can we get the video? Yes, of course. You will get the video by mail after the recording. There is another question. What about the reproducibility of the calibration? Is the reproducibility related to the uncertainty? So reproducibility means, by definition, that you remeasure a sample over a long time and with a lot of parameters you change, so that you include all the errors in that reproducibility. And then this is one part of the uncertainty. The reproducibility will not take into account the bias. So how true is your calibration? Yeah, what is the difference between true values and the measured values? So this you have then to add also to get the complete uncertainty. Okay, any more questions? No, then like promised, we will send you, of course, the presentation and the video, the link to the video. And if you have some more questions later on, you're always welcome to send me an email. And then I hope that you got some valuable information in our webinar today. And I thank you very much for listening, and I wish you a nice day. Thank you. Bye-bye.